Today, I'm going to give this presentation that is called Engineering Practices Break Music Interaction. Kind of like a little bit of like a clickbait, if you wish, but can also fix music interaction engineering practices. So the whole idea here is like I'm going to be presenting my whole PhD journey. I'm finishing a PhD right now. So where I have been designing synthesizers with sound-based control based on neural networks, and that these synthesizers are intended to be used with musical instruments. So my idea here is to share my experience working from an engineering standpoint, and then, which is, I believe it is really common among us, and then I want to tell you how did I open up to an alternative form of thinking, of form of view, some problems that is really important for interaction. So let's just start, and I'm going to give you like the outline for this presentation. I'm going to give a very brief introduction of my PhD, where I design sound-based synthesizer control with neural networks. I'm going to tell you my first approach to design a sound-based synthesizer with AI from an engineering standpoint. I'm going to tell you also how I was exposed to like alternative views on the problem, how this helped me to gain actionable feedback to iterate from an engineering standpoint again after I switched it for a while, then I came back to an engineering standpoint, and then some takeaways which I believe are important for interaction that I learned during my PhD. So about me, I'm an electronic engineer from Argentina, and I did a master in computer vision, and I'm finishing a PhD, as I was telling you, at Queen Mary at the Center for Digital Music, together with the Augmented Instrument Lab, which is now based at the Imperial College, and I'm a musician. And I think these two pictures show, may set the tone a little bit for this presentation, because yes, I play guitar, that's my main instrument, but I'm a technologist and I love over-engineered stuff, right? That picture there with the old Yamaha DX5, which is like a very oversized keyboard, and a Polaroid camera, which is one of the most over-engineered devices I ever seen in my life. So probably it will set the tone for what's about to come. So yeah, that's me. And my project, well, my project is about controlling synthesizer with sound. You could also call it timbre transformation if you wish. And the whole idea here is that, I play guitar, so I want to connect my guitar to a computer, get the audio from my guitar to a computer, and I want that computer with a neural network to generate audio that perhaps has a different timbre, but of course the same content. If you wish, the same melody, the same chords, the same timing, the same rhythm. And well, by the time I started my PhD in 2021, mid-2021, there were perhaps like three main approaches for sound-based control of neural networks. And the first one was the tone transfer, or the DDSP approach, where pretty much these all networks are audio to audio, right? So you have an audio input, you try to capture, for instance, the fundamental frequency and loudness of that input, and then there's a neural decoder that maps that to a synthesizer, and we have an audio output. So it's a synthesizer controlled by an audio input. Then we have, for instance, like the system for like cloning audio effects. So if we have like dry and wet data, we can actually train a neural network to simulate that effect. And then a few months after I started my PhD, we got this rate model from Arkham that we're going to see later. But this model also works in the same way, right? There's an audio input, an encoder that extracts some information, and then a decoder that generates sound based from that information. So, okay, then, research doesn't occur in isolation. So when I started, there were multiple reasons to try this tone transfer model and try to make it, more suitable for real-time operation with musical instruments, right? To make it lightweight, lower latency, to make it real-time so that it can run in a variety of systems. And again, I was telling you, I play guitar and I love FM synthesis. So it's like, perhaps is there a way to combine these three, if you wish, intents on specifications to make something interesting and something that is playable with musical instruments. And there go 2 years of my PhD. So it's like the whole idea here that I want to explain is that, okay, you take a design decision, and then that unravels into a crazy amount of technical engineering work that you have to do, right? So it's like the whole idea that I want to take you through is like, what kind of technical challenges did I buy into when I chose to do this approach? And by the way, this is not a technical talk. The technical talk that I have given about design and inference of neural network was 2 years ago with my colleague and friend Andrea Martelloni. So if you want the technical stuff, the technical side of this, you can take a look. But here we're talking about design decisions and then technical challenges that emerge from that. So again, I went all in. I went all in, you know. So I decided to do tone transfer with FM. We have an audio input. We have a set of measurement algorithms that extract, if you wish, fundamental frequency and loudness. We have a neural decoder that predicts some envelopes. And then we have the FM synthesizer that is driven by the fundamental frequency of the audio input and then the envelopes of the neural net. And we have an audio output, right? And well, we have a loss function. We have a loss function that, you know, perhaps we can put it there or put it in some other place, but that's pretty much the specification that I decided to do, right? So it's like, again, you buy into a problem, you take a design decision, and now you kind of like start thinking, how do you build this? Up to what specifications? So you start to think of dataset selection, you know, whether the architecture you want to make it lightweight and cautial, so to make it lower latency. You want it to run it in real time, so you need an efficient implementation. You need to select a loss function, right, that maybe is like in the audio side, on the parameter side. You need to decide whether you're going to backpropagate or not through FM. You know, and then at some point you need to like develop a plugin, right? And 2 years of my PhD, right? It's like trying to solve these kind of problems. But of course, as a musician, like my objectives revolve around different ideas. These ideas that are related to music, to aesthetics, to embodiment. You know, the fact that when I play guitar, it has to feel like a guitar. So I want to play melodies with my guitar. I want to be able to execute different articulations. I want to access to a wide variety of timbre because, come on, like I play the DX7, the DX5, so it's like so many varieties of timbre that you can do. Of course, I want to intervene the FM synthesis process. And I want to transfer skills from my guitar because I'm a pretty lousy keyboard player, but not as bad as a guitarist. So it's like I want to transfer my skills from the guitar to the keyboard, right? And there you go. I ended up building a plugin, right? After, you know, I did like 3 papers on FM synthesis with neural networks, and after some point, I had this plugin working. Fantastic. So the question now is like, in theory, this was working. I can show you a video, I will show you in a second, a video, and it is working. The test set of these neural networks and all the tests that I ran, they seem suitable, right? They seem okay. I actually got it published 3 times, you know, different implementations of this idea. But, you know, the plugin seems to sound okay, and the idea seems to be sensible for an engineer, right? But let's review it only one more time. So we have an audio input. We're applying some measurement in order to extract some features. Those features go to a model. Let's just say that the model was trained with violin data, right? So guitar features that we are like, you know, theoretically isolating timbre and capturing content. We train this model with a violin. Then we go with an FM synthesizer. It's also configured to sound like a violin. And we have violin, right? So when I pick up the guitar, finally, after 2 years, and I build this plugin, shablam. You know, all the design decisions seem to, you know, come back at me, right? Seem to conspire with me. Because it's like, I found that even though the test sets were okay, I found that there were missed sounds, right? Sounds that I could do that were not sounded on the synthesizer. Ghost sounds that would appear out of nowhere. Some sounds had wrong pitch, and there was variable lag. It's kind of like you design something, you try to make it work, and then, you know, you take a bite out of it, you model as you want, and these things kind of like bites back, you know? But yeah, I could still play it, but it was pretty difficult. And it feels completely anti-natural. So let's take a look at one example here of me playing. I mean, I hope that was sounding okay. I hope that it was clear, okay, because I'm getting some weird feedback here. But yeah, it seems that you can play it, but it doesn't feel at all like playing a guitar, right? And it was really difficult, very anti-natural. So it's like, what was happening here? What are those bizarre failure modes that we're having here? So it's like the system seems to work, but again, there were some ghost sounds from ancillary movements. So if you describe it, and this also was validated by some musicians that I ran like some tests with it. So I play the guitar, right? And at some point I'm just moving my head across the fretboard and boink, some sounds come out of nowhere. They come out, not out of my volition, if you wish, right? Those are ghost sounds that appear out of nowhere. Then I have like relatively high and variable latency, even though like I had worked so much to reduce it as much as possible. When I was playing really fast, I would get some sounds that were missing, right? I would play really fast, and some of the sounds that I was playing, they were missing. And very, very soft sounds, they would also be missed, And you can tell me, okay, this whole system is designed around like a fundamental frequency tracker. So what I can do is like, that kind of like sets the tones of each of the events that's going to happen. And it has a periodicity threshold. I don't know if you're familiar with the gene algorithm or other newer fundamental frequency trackers, but pretty much you have this periodicity threshold, right? And it feels that if you were able to adjust it, then you can find the right solutions so that it works great. It does not. Because again, like this kind of like a, you're cutting here, but the problems happen in a different dimension. So it's like if I set the threshold really high, then I don't have any unexpected sounds, but some of the sounds that I want to do, I cannot do. And if I set it really low, then it's the other way around, right? I can do all the expected sounds that I want to do with my guitar, but I also have a plethora of boing, bang, bang, like sounds out of nowhere that appear. So yeah, it was impossible to play well. And we need to search for, somebody like a guilty character, right? Not me. We need to search for some accountability, if you wish. So it's like, why did it fail? Why did it fail? Because like from an engineering standpoint, it was a practical design based on some other, like research papers. It did converge the training did converge. It had good quality metrics, otherwise it wouldn't have been accepted. And it is efficient and lightweight. So it's like, well, maybe we can, increase the fundamental frequency accuracy, make it like a neural fundamental frequency tracker. We can make it polyphonic. Sounds interesting. Then we have like, opinions from myself as a musician and from other musicians that they cannot play it well. It does sound okay though. Let's make it more responsible. It's like making it more responsible. Like, to me, that's non-actionable feedback. It's like, of course, I don't know what to say. Yes, let's make it more responsible. How? And then, working as part of the Augmented Instrument Lab, I was really, really lucky to be exposed to some alternative forms of thinking. And in some of HCI papers, you can actually read it in this way, which is kind of difficult, right? It's like the epistemology becomes the ontology. And for us engineers, sometimes we take an HCI paper and it's completely unscrutable, right? It's really difficult to read. That's why the character there has like a hard thinking cap and a dictionary. So just bear with me for a second. Let's take a step back and try to understand this, in more detail, because there's a good opportunity that we can actually reflect about the things that we do here. I'm going to give you a very, very narrow take on agential realism, which is a theory of existence, of ontology, of knowing, that was developed by Karen Barad. And pretty much what this theory tells us is that there are no hidden truths waiting to be found. And we can really, really quickly, attach it and apply it to our problem. It's like when we are trying to measure something or when we are trying to model something in language, well, that thing that we model only appears when we model it. The apparatuses that we use to measure something don't extract it out of the universe because it's not waiting to be found. It's something that is created, almost kind of like now in the AI era, we could call it hallucination, if you wish, right? So it's like what it tells us is that, again, these measurements that we extract, we are not really extracting them from the universe. The universe is completely indeterminate. So we just create this out of nowhere. And when we measure something, we establish what is called as an agential cut. And that is the moment when, like this indeterminacy collapses. This theory is based on particle physics, right? It's not based, it's inspired by particle physics. Pretty much what we're trying to say here is that we have to contest the meaning of the language that we use to talk about representations because they may not really represent what we mean. And let's bring it down really, really close, really, really quickly, sorry, to this particular problem. And this is what I call the material stance. So the representations that we use, in this case, fundamental frequency and loudness, are not constitutive qualities of audio signals waiting to be found. They are local, they are not interoperable, which means that they can work really well in one situation and completely break down in another, even if I have like 100% accuracy fundamental frequency tracker, yeah. They are not truly separable from each other, which means that I'm trying to measure an audio signal, and I measure the fundamental frequency, I measure the loudness. Those things are actually not separable because they are not quantities waiting to be found. They are not separable, which means that they are entangled and they are related to each other. And that relationship can actually, explode in our faces when we don't consider it. So as materials, these representations have agency on the outcome of the system. They enforce a perceptual system, which means that when I'm measuring something as a representation, and I'm saying, okay, fundamental frequencies, I'm measuring them, I'm actually just blocking that as the only form of existence that can happen. So only the things that comply with the expectations of that algorithm can only exist as an output from my system. And I'm blocking everything else. It forces you then as a musician to comply with the algorithm. You stop playing the guitar, and what you play is the fundamental frequency tracker. So it doesn't feel like a guitar anymore. And they are put there by engineers because they have nice names, right? The loudness, the fundamental frequency, then it's like, just connect everything together and it works, right? So they are really tempting, right? Because it's like, okay, I can derive meaning out of it, but you don't derive meaning, you create it out of nowhere. So it's like, they are put together there in order to make sense of the world, make sense of this audio signal that I'm playing. But the big problem is that, the events that we capture that are ambiguous are completely shifted apart. So that's what we call ambiguity shift. Even though we put it to stabilize a system, the system completely fails when it's presented with ambiguous information. For instance, ambiguous pitch. So that's a paper that we did with some of my colleagues, with Adnan Korni and Andrew from the instrument lab. So again, it's not about the specifications, right? Playing music is an embodied act. It's contextual, depends on the context. It's ambiguous because some sounds can ascribe different meanings. And it's noisy, of course, because it's like we are, in a sea of noise. And then we're trying to collapse all of that into like very clean, fundamental frequency and tracker, which are absolute characteristics, right? Fundamental frequency, we measure it in hertz, very absolute. Loudness, we measure it in dB, right? And they are B-stable because they can either be detected or not. So they are actually discrete, if you wish. So it's not a matter of just improving the specifications of a representation, because again, the epistemology becomes the ontology. What does that mean? What I think I know becomes the only thing I know. What I think I know becomes the only thing it exists. That's what I want to say. So what I think I know, I model it in the system, and that knowledge becomes the only thing that can exist in the system. So what matters is what the representation brings into reality. It's not a question of improving the representation, but a question of criticizing, and thinking about the representations and what kind of events bring to reality. And what is the treatment of ambiguity in this case? So let's take a look at a very quick example and showing how, these things are not separable. And when we consider, for instance, content and timbre, right? We were saying that timbre is isolated and we have content, on the system. Well, let's take a look at something here. I build this like synthesizing MIDI, so we have a ground truth here, and I'm using like the state-of-the-art MIDI tracking, non-real-time, no causal, the best possibility that can have to measure and to find the ground truth, if you wish, right? So it's like, let's do this one first, with the sound of a guitar. Did it sound well? Fantastic. Let's do another one. Let's make them all very quickly. This is a Rhodes piano. There you go, and that's strings, right? So if we take a look at the acoustic guitar, this state-of-the-art MIDI tracker actually seems to have captured all the notes, but they don't capture it in its full length, right? If I took a look at the Fender Rhodes, right? Well, we have one missing note there, the C4, and then we have two notes out of nowhere, kind of like ghost notes that appear, right? And the strings, well, you have some phase cancellation when you render all the strings at the same time. So what we have there is like everything is done in the default settings, right? What you have there is like a bunch of nodes that come off and on. So it's like, this really shows that there is no ground truth here, Like, this is entangled. This kind of like ground truth that we're trying to extract is actually entangled with timbre. That's why with different timbre, what you get is a different measurement, even though what you're trying to extract is content that we believe it is separated from timbre. It is not. Let's take a look at another example here. For this example, I don't have MIDI, but this is an example of like a muted guitar being played, right? Well, and that's the MIDI output. Pretty poor, huh? It's like definitely not following all the notes, all the sounds and events that I do with the guitar. Great, this is a state-of-the-art system, by the way, and I'm leaving it in the default settings, which are the settings that should work the best, right? Of course, I can tweak it, for each different example to make it sound better or more accurate or whatever, but that also gives me the clue that results are local. They are not interoperable. If I need to modify the MIDI tracker for each example, that means that I'm not capturing any ground truth, right? Fantastic. And these things may sound pretty obvious to you. And for me, they were not obvious. But they were not obvious either for these people, right? The people at Google Magenta and ByteDance, we actually put out plugins out there, based on fundamental frequency trackers and DDSP, and nobody ever downloaded them because I haven't seen a single person using them. Anyways, so, this really calls for, examining engineering approaches, because I think it's a problem that is much more generalized than only me, which, I just didn't see it before. Great. So if representations are local, which means non-interoperable, and completely unrelated to music cognitive processes, then why do we keep on trying to measure them? Because, again, there's a loop of action perception when I'm trying to play guitar with this thing, right? We have the measurement side, the synthesis side, the output, and of course, all these decisions can kind of like bite back to me. And, this analysis measurement, pretty much what it does is like it put this, it's not a filter, but it only brings to reality the things, that I know they are true, okay? Epistemology to ontology. So there's a lot of actions that I do that have no output, And there's some other actions that I didn't do, like that arrow there that appeared out of nowhere. So the question is, wouldn't we be able to create a representation for pitch and loudness that has some space for ambiguity? Because if we have some space for ambiguity, then maybe we can actually leverage that to make a system that feels more natural to play, right? So back to square zero, again, engineering, trying to find one of these architectures to use, and we have Rave, that many of you probably know. So Rave is this architecture that again, like learns a representation. It doesn't have a fixed representation. It learns a representation in the encoder, and then it learns to generate audio from that representation with the decoder. So Rave. Great paper, great people from Arkham 2021. It does really expressive timbre transformation possibilities. Some products actually are based in this architecture. And it has seen extended use for live performances. Yes, it has higher latency. You cannot use it directly with musical instruments. But there's also something much more worrying to me that happened after Rave, and it's like the complicated design trend that followed. So if I want to show you just Rave and two more autoencoding systems, because this is an encoder-decoder is an autoencoding system, you have, for instance, the script audio codec and the stable audio open autoencoder, and what you see here is like they're always trying to have a higher number of parameters and higher compression ratio, which pretty much what it means is that the compression ratio kind of like defines the buffering of the system, so it increases the latency. And well, why is this happening, right? Because newer systems have higher latency, which means it's more difficult for musicians to play. And it's just that the general application here is like we train this, right? We show an audio input, we have an audio output, we train it, we get some highly compressed latents, right? Maybe one time step of this representation there can decompress into like, I don't know, like 4,000 samples of audio, right? And this is because after it's trained, they just strip out the encoder, and they connect an LLM, and you have text to music, right? So it's like, this is pretty cool, and LLMs really struggle with the length of a sequence. So that's why you want to have audio that is has a problem, dimensionality problem in terms of samples, to have it really compressed. And yeah, the rate for generative algorithms operate in this latent space, right? But for musicians, it's a different thing, because we need 10 milliseconds of latency and 3 milliseconds of jitter. So, rate can operate in real time on CPU with some latency, and the others, they seem even to be more complicated to operate with in CPU with low latency in a streaming approach. It seems to be worse. So it's like, this is when engineering actually comes, to save the day, if you wish, because now that we understand the problem, we can actually work against the threat, right? And it's like, well, the rule is 10 milliseconds of latency and 3 of jitter. Fantastic. So let's go into study the sources of latency. This is a paper that I did with my friend and colleague Jordi Shire and our supervisors. So we studied the sources of latency of rave. We addressed this with an architectural redesign for low latency and jitter. And then after that, I actually coded this network in C++ to make it really, really efficient as possible, to make it work really, really efficient, and to make it suitable for real time, right? And well, we came up with this model that's called Brave, and in comparison with Brave, this is the only technical slide. You don't really need to pay attention here, but this is the world of specifications, right? The world of engineering. So pretty much what I do here is I change the specifications and I design with some other specifications ideas. That's how we engineers operate, as far as I understand. So it's we have a lower filter attenuation. There's a bunch of specifications, right? Smaller and kosher load encoder, lower compression ratio, simplified output scheme. We have a similar audio quality with reduced latency, and also we have improved content preservation because, of course, we are running with a very small, let's say we're running with a small latent space with a small compression ratio, which means that we have more space for temporal resolution, right? And the best thing of all is no prompting, right? Because with such a small latent space in terms of compression, an LLM would struggle like crazy. So there's no automatic music generation. You need a human being on the other side, playing guitar or playing something in order to make it work. Fantastic. So does that mean that now we are free to roam? We have, broken the chains of representations and engineering just because we're using an autoencoder? I see some people saying no. Fantastic. You are paying attention. Thank you. Yes. No. We have a feature extractor in the encoder. We have a generator on the other side that is generating audio, right? And we have a representation in the middle. Yes, this is a learned representation, a latent representation. You can call it latent space. Woo, it's the same, right? But the great idea here, and of course these representations I'm going to do an agential cut. They're going to exclude some information while bringing to reality some other information. But to me, the great thing here, and the great opportunity here for fully neural systems, is that we can work with representations as a design material, and we can iterate over it, and we will always, or in the best, in lots of cases, let's say, we will be able to invert that representation into its generative components using a decoder, also a neural decoder. So we can work with representations as design material and perform this kind of iterative work. Again, I can tweak the encoder, change the training data, change slightly the architecture to make it work better the way I feel, right? There's no specification to tell me you are going to play guitar great, But the way I feel, and I can work with it as a design material. In other words, make it sound good, make it work well. And I know that if I do that, I can also invert it into audio anyways, and I can still use the same training data. So it's yes, this is an iterative process of, it's called as resistant and accommodation. And there's a big opportunity here because representations, neural representations, and are easy to invert into generative primitives using a neural decoder. But of course, there's a risk because these representations are latent. So at some point, we may even forget that they exist. And we're going to start thinking that the only reality possible is the reality that affords those representations because they can make music. So there's a risk there. We still need to have a stance, a critical stance toward representations, right? It's only a part, it's not reality, it's a collapse, of reality that is created. Anyways, let's try some types of representations here that I want to show you for a second. I want to show you this example of my friend Aidan playing playing guitar, and you may see here, let's see. You may see here that there's like some ambiguous pitch, there's some harmonics going on with the guitar, and we will see how these sounds are treated by 3 different representations: the pitch and loudness, the first Brave model that I trained, and then another model that is newer, that is actually being worked on with this material stance. Hopefully it sounds okay. Let me add a little bit more volume. So this is the pitch tracker, right? The pitch tracker and the fundamental frequency loudness, and you can see that the harmonics, first of all, it didn't pick it up because they were too soft, right? And then we have like a bunch of wrong sounds happening around it. Let's take a look at the other one. So this one sounded a little bit better, but if you pay attention, there's a few notes or sounds that had wrong pitch, and some sounds that were completely rejected by the system. So again, we are incurring in a representation, so we have these problems. Well, this actually sounds better. Like I hope you could hear. We're running a little bit long on time, so it's like I'm going to continue, but I can show you later some other examples that I have. But at least to me, it sounds better. And it's not only a question of sounding better, it's the question of how it feels when you play it, right? That's even more important. So, okay, some thoughts and takeaway for this system. Let's remember, technology is not neutral, and it's always enacting this agential cut that happens between the measurement and the apparatus that should be measured. So we need to be very careful with design primitives, because as soon as we take a design decision, we buy in a pretty large set of beliefs and technical challenges that unravel out of that. So it's like, again, technology is not neutral, so we have heard it too many times, right? The kind of classic complaint here is like, boo, we have the CQT representation that assumes an equally tempered scale, and we have MIDI has only 127 notes to explain music. Yes, that's fair enough, right? But let's take a closer look at other design primitives that we use as if they were neutral, right? For instance, let's say that I want to make a sound-driven synthesizer. Fantastic. I'm going to use a synthesizer which is a bank of oscillators, right? They're pretty neutral. No? I can create any sound with a bank of oscillators. I could even do wavetable, right? Wavetable synthesis is an oscillator. Fantastic. Those oscillators require an envelope generator, right? Okay, nothing wrong there. I need to somebody has to vary the volume of those oscillators to make some timbres interesting, right? And well, maybe you could criticize a little bit more this decision of putting an audio input, having the fundamental frequency and the RMS capture in order to block timbre out of it. So again, the problem is that the bank of oscillators assume an explicit oscillatory frequency in hertz. So that's already forcing me to have in my system an existence of a really clear fundamental frequency. The envelopes assume a discrete musical events because somebody has to trigger them. So it's they're either off or on doing the envelope. And of course, we have this idea of separating timbre as a measure quality, right? So technology is not neutral. Oscillators come from where? From the dawn of communications in beginning of the 20th century. And we needed oscillators with a really certain frequency in order to have a communication channel so that we could a common channel to communicate. And of course, assuming discrete musical events and separating timbre It comes from, the age of classical music, if you wish, right? Of music writing. So my supervisor, Andrew, has a paper with other colleagues that talk about like the original mapping, the original, tangential cut between sound and notes. And it's the music sheet, if you wish, right? It's kind of like the original scene about it. It's really funny. Anyways, there are opposing forces when you design. You need to take a lot of decisions, right, that can unravel into technical hurdles. So if we look at it from a specification point of view, so we need to look for metrics to improve and measure more, right? Improve the agency of these measurements. Try to make it higher accurate with higher accuracy. On the other side, there's people that like to run user studies, right? And it's like, well, you run user studies to try to validate the affordances of the system, and then like if you have nothing to say of like any actionable feedback, yeah, perhaps you didn't do the right user study. And then you have, the material stance where the epistemology becomes the ontology, and it actually tells you to measure less, to leave more space, to let things come to you and in a more ambiguous way. So it's like telling you to measure less. It's like, what do you do in that sense, right? Because all in all, when designs do not meet expectations, you may even don't say it, right? Because you can say, yeah, I tested a bunch of musicians and they give it a scale, 7 out of 10. Great, pat myself in the back. So it's like, which perspective was responsible to this failure, if you wish, or to this break of expectations, right? Who are we going to blame? Well, none of them. It's probably you, it's probably me, right? But that's okay, because this is a learning process. And the important thing is like engineering gets the thing done. But there are specific times where you may want not to think as an engineer, just for a bit, right? And then we can go back to our trade. But that's okay, it's a learning process, right? So it's like, I'm going to share a few takeaways with you about the opposing forces. When working with AI from a technical stance, right? Well, we can see that we fit a data set that the model is learning, but sometimes we need to question the representations. Again, the fact that you fit a data set doesn't mean that you are fitting your expectations, right? Also, when we think about better data, right, or higher quality data, yes, with higher quality data, your algorithm may sound better, but it may be as unplayable as it was before. Because again, better data does not imply better interaction. We need to take a look at the representations, same thing. Representation ratings, when we are, take our shopping bag and we go to see the latest algorithm in GitHub, and we pick up, a representation with a higher accuracy. Somebody's laughing over there. Okay, good. I touch a sensitive nerve. Love it. So they refer specific context of use. They are local, which means that they may work really well in one side, and they may fail completely in another situation. Remember that every time I put a representation, I'm enforcing a locus of meaning, a locus of perception, something that the system wants to see. And if it doesn't see that, it gives me nothing. So that will compete against the musicians who are trying to play it. And that may actually coerce musicians to start playing the way the algorithm wants. And remember that we designed these systems to have really clear meanings as engineers, but because we want to make them stable, and we want to make them low latency so that they are responsible. That doesn't mean that they will have volitional control because of the representations that we put there. And again, this is the sad part of it. You can iterate over a design and be a rabbit hole if you don't get, to the core problem that maybe is your representations. Again, to think about that, this is some food for thought. This is a paper by my supervisor, Andrew McPherson, that talks about, notes aren't real. So it's like the fact that we shouldn't design musical instruments with the ontology of notes inside, because musical instruments create sounds, do not create notes. So I decided to extend it a little bit, right? Kind of like, if we think about food, how can you call it, certification? Well, we could certify that our synthesizer has no notes. Great, because again, the epistemology becomes the ontology. It has no fundamental frequency because it's just, it's like a MIDI pitch bend, right? And it has no triggers because there is no discrete events that happen. Everything is continuous. and it has no oscillators, because the oscillators actually are asking for all the other things before. And how fun does this sound, right? Certify, yeah, it's freeform oscillators, come on, that's great. So some posterior work before finishing. I'm trying to facilitate access to this technology of like sound-driven synthesizers, been working a lot in improving audio quality, diversity, and efficiency, and I'm working in collaboration with some musicians and composers, so please contact me if you're interested. And I'm really happy to present Mini Fusion, which is a system for timbre transformation, for running synthesizer from audio and transforming voice, and it's available for downloading. You can run it with voice, with guitars, with different instruments. So yeah, if you're interested, please take a look. And we're going to do a very quick demonstration here, just to see. This was at Sonar Festival. Two musicians popped by my stand, and without even knowing the system, they started to jam. And the system is really responsive, if you wish. It's really intuitive. And there's a woman singing and converting that to saxophone, and a man transforming the guitar into electric piano. DX7 electric piano, by the way. Yes, so, by the way, this was electric piano, but not with the FM synthesizer, right? This is all using Mini Fusion. And to make it even more risky, let's gonna try to do it live now. I'm gonna try to give you a very, very short demo live. Let's see if it works. Hopefully it will. Okay. Yeah. Well, it doesn't show, but I can show it to you anyways. So I have yeah, I can show you anyways. I have a system that transforms, for instance, voice to drums, and it runs in real time. Well, that's it. Yeah, thank you. Oof, thank you so much. Well, that's pretty much it. If you have any questions, please come and see me. Thank you.